Hi, thanks for listening to our presentation on SALTED. My name is Vikas Ronak. I'm a research scientist at Microsoft, and this is joint work done with my colleagues Matt and Arun. The name of the paper is based on the superstition that if you salt a bird's tail, you may be able to catch it. The birds in our case are errors in state-of-the-art empty systems. Before describing the paper, here's some motivation behind it. Consider this English to German translation pair. Here, 6 feet gets translated to 6 meters. And we know why this happens. This behavior is learned from the parallel data. In fact, for most of the failure modes in NMT, including hallucinations, we have a good mechanistic understanding of them. But yet, as we show in the paper, errors in the translation of such salient content are quite pervasive in state-of-the-art empty systems. And we believe that this reliability bottleneck is there because we don't have any fine-grained measurements beyond average case performance. So no matter how we iterate, over an empty system, we don't have visibility into such problems during development. And even though the metrics we use are getting better, the assumptions behind metric themselves do not allow targeting reliability explicitly. These assumptions include joint fluency and adequacy modeling through a single dimension of translation quality and no explicit notion of salient content. Here we argue that for improving NMT reliability, we need to augment metric-based average case performance evaluation with multidimensional, fine-grained measurements of salient errors, which could make these previously hidden problems visible during model development. Before we describe our approach for this goal, I'll talk a little bit about the nature of errors in NMT that precludes us from using some existing techniques. For example, checklist is a popular evaluation methodology for behavioral testing of NLP models, which builds test cases for different capabilities. However, it does not generalize well to NMT, as there could be multiple valid translations of the same input. Typically, the errors are rare. Vast amount of test cases would be required to elicit such long-tail errors. Errors are highly contextual. Fixed test cases cannot capture this, and error distributions across model or data iterations change. So based on the nature of NMT errors, a framework that tries to provide these long-tail measurements should address at least 4 concerns. First, it should provide targeted error measurements at the instance level. It should be scalable to address error rarity. It should be invariant to the unstable model error distributions across model or data iterations. And finally, it should provide trustworthy measurements. So here's the SALTED approach. It is a methodology for obtaining measurements through behavioral testing by building detectors. It leverages monolingual data and relies on specifications of correct behavior in order to build those detectors. A detector is just an algorithm, a program, which given an input-output sentence pair returns a Boolean value indicating the presence of an error condition with high precision. Before we describe the process of building detectors, a note about behavior specification. First of all, this is a fundamental step. If we cannot specify correct behavior, then we cannot verify output correctness. But there could be ambiguities in describing the correct behavior, in which case the choice is left to the model developer. For example, even for the simple case of physical units, the choices could be whether the empty system should convert units or not. Either specification is plausible. In our work, we choose the non-conversion of units as the correct specification. So here's what the process of building detectors look like. We start with system outputs on a large monolingual dev set, and we iterate on the detector program until absolute precision is achieved through human evaluation. And finally, we conduct a test phase evaluation with a different monolingual data and system output set. So at each iteration, any of the 3 components of the detector, the specifications, the resources used to build the detectors, or the detection algorithm itself is subject to changes with the goal of moving towards high precision. Using this process, we build detectors at both the token level as well as the sequence level for multiple different error categories, which we consider to be salient in terms of their disproportionate uh, impact on the users. We emphasize on high precision so that the measurements are trustworthy. For example, here is the precision of the detectors we constructed in its test phase. We elicit a number of errors using these detectors by just passing monolingual data translated using different systems through these detectors. So here, this slide shows some examples obtained from some public NMT systems. We find that these long tail errors are quite pervasive across different systems, even though their incidence rates are quite low. And here are some instances obtained from the WMT21 winning system. And what this shows is that there are still inputs on which the model fails catastrophically, even though it obtains really high average case performance. So what we have established so far is that the proposed approach is useful in eliciting errors and obtaining measurements of those errors. And next, we show that there are other use cases for detectors as well, such as data filtering or synthetic data generation. For the data filtering experiment, we trained 3 systems. The first one with no data filtering, the second one with a standard filtering algorithm applied, and the third one with the filtering done using the high precision detectors built by us. So the first thing to notice here is that detector-based filtering throws away about 5 million less samples than standard filtering and obtains higher average case performance owing to that, whereas standard filtering is comparable in terms of its performance on the long tail measurements. Another observation is that through these detectors, we obtain a trustworthy view into these long tail errors during system development itself. So for example, even though the standard system obtains lower average case performance than the unfiltered system, uh, the detectors show that it is obtaining far fewer errors, far fewer salient long-tailed errors. So another use case of detectors is in generating novel data either for testing or for error correction of certain token level errors. So for testing, we generate multiple novel error instances just by generating synthetic data using the detectors. Similarly, we also generate data that is used to fix certain error types, such as the incorrect translation of physical units. And these the synthetic data generated by the detectors is used via a fine-tuning step in order to fix some token level salient translation errors in our system. So to conclude, we proposed a framework for obtaining long tail measurements of some salient error categories in machine translation. We showed that the same framework is amenable to a number of use cases in MT, such as data filtering, metamorphic testing for fixing errors, a process we named metamorphic fine-tuning, as well as just for general behavioral testing to elicit different error types. So do check out our paper, and thanks for listening to our presentation.